This is Statistics 243 for Friday, October 4th, the 15th class of the fall 2014. Okay, let's go ahead and get started. So I wanted to pick up where we left off last time. Folks, can I have your attention, please? Okay, so we left off when we were talking about copying and when copies are made. And we've already seen a couple of cases where either code is not evaluated when you're passing code in as an argument of a function until it needs to get evaluated. That was the promises in the lazy evaluation. And we're also starting to see that sometimes copies are not made of objects when you might think that they would be made of them. And so, just to recap from last time, we already saw this here when I changed the names of the arguments here, just to make this a bit more explicit. That if we have this function f, it takes arg1, and then we're going to print out what the memory information is about that. And so if I do internal of inspect of x, so this is the object on the outside in the global environment. And now if I do my f of x, what I should see is this printing out here corresponds to the printing of the information about the internals of the object for arg1, and you can see that it's pointing to the same place in memory as was the original x here. Okay. So at this point, because x, the arg1 in the function has not been modified in any way from the original x, there's no reason that r needs to make a copy, and it's actually smart enough not to make a copy of that arg1. And in fact, we could go ahead and do some processing on arg1 as long as it doesn't change values in arg1. And in general, no copy would be made. It would just be working with the elements of x in this particular memory location. So were there any questions about that from last time? Okay, so we could think about this a little bit more. So suppose now that I take x and I pass it through as.numeric. So I cast it from its current class, which is whoops. I guess sorry. I have to remember that I'm doing things over in the R session here. Okay, so it is already numeric. So now let's suppose that I am going to run this function, but as I'm doing this, I'm actually going to first coerce it to be numeric. So this might seem a little bit silly because it's already numeric, but it'll be interesting to see what happens here. So the two things presumably that could happen are either that somehow a copy gets made because of this casting, or R might be smart enough to realize that you're casting it from a type that it already is, so there's no reason to actually have to do any copying. And so if we do this here, we see, okay, it looks like this has not changed. So it's still the C870 down here. So even though we've tried to cast it, R was smart enough to realize there's nothing to be done here. Okay, so what do you guys think is going to happen when I do this? When I take x, which is numeric, and cast it into an integer type? So does anybody know anything about storage? We haven't really talked about this explicitly yet, although we'll get to talking about this in much more detail. Does anybody know about anything about storage of integers versus numeric real values in C or some other language? No? Okay. So in general, if you're storing a real number, you're going to store it in 8 bytes, which we've talked about. Integers, at least the way that R stores them and that are in general stored in a lot of other languages, is they're stored as 4 bytes. So they're going to take up half as much space in memory. Okay. So given that, can anybody speculate as to whether a copy is going to be made here? Eugene?
Casting data type, it should change it's smart. It should change the copy because otherwise you're going to be truncating your values.
Yeah, and in fact, I'm not even sure it's, I mean, I'm just sort of quibbling with your words here, so I apologize for that. But in fact, it's not even just that it's smart, it's that if we're thinking about storing numbers and we've got an 8-byte storage area for a real number, and that's true for this entire vector of values, and now we think about, well, we want to store them as integers, I'm not even sure there is a way to go in here and basically say, oh, okay, instead I'm just going to use up half of this region for storing the integer. So there's probably not a way for the operating system to do that. And in fact, if it did that, you would now have values in the vector that were no longer contiguous in memory, because there'd be the 4 bytes and then an empty space and then the 4 bytes. Okay, so in some way or another, there has to be a copy made as a result. So hopefully we'll see that here, and I won't have contradicted. This won't contradict what I'm saying, although occasionally we've seen that does happen. Okay, so here you can see that indeed this is a different memory address. It now says it's an integer form of one of these S expressions instead of the real form, and this all makes sense given what we just talked about. Yeah.
So one of the tricks, as far as C is concerned, you have an array of numbers, right? You cast them as integers or as a smaller thing that they're stored as. The program is like, well, I guess what he's doing, let's do that. So basically, you essentially get twice the number of integers as you had real numbers. But each one would be as seen as half of the bytes of the original.
So maybe you may know more about this than I do. I was sort of saying over there that I didn't see any way that one could
do that. The way memory works is, it knows that an integer is 4 bytes.
Right.
So it moves the memory location by 4 bytes every time. So if you didn't make a copy and just cast the whole thing to integers, it would be moving half through the numeric thing.
Yeah, I mean, if it were doing that, then it's going to be interpreting the second half of it, and it would be garbage.
Exactly.
Right?
So it has to be a little bit smarter.
Right. So I mean, in ours case, maybe there might be other things going on in other languages that I'm not as familiar with. In ours case, there is a totally explicit copy made. It gets put in a totally different place in memory, and now it's taking 4 bytes per value.
Can you trick it?
Can you what?
Trick it?
I don't know. I suspect not, but you might be able to. Okay, so the other thing I wanted to go back to from last time, and I think I have it. Oh no, I guess I already lost it. It was further up here. I was running it a second ago. So we had this question of, I was trying to figure out if we are thinking about the storage of a vector, and this is the memory address for that vector x, and I was sort of hemming and hawing about, is that the first position in the vector, or is there some like meta information stored first and then the vector is stored, the actual values of the vector are stored after that? I'm still not totally sure of the answer to that question. But it's interesting to look at this. If I do this, it says, okay, that's where it is. If I do this on the first element, it says, oh, that's where that is. And this doesn't seem to be at all related to this. In fact, I can't really count in units of 8 and really get here. This is a long way away in terms of memory from this. So it's suggesting there's something weird going on in terms of if this were reporting where the first element was, it seems kind of weird relative to where it's saying that the overall vector is stored. But there's something even more interesting going on. Okay, I'm going to repeat this call again, and I get the same answer as I got here when I do the internal inspect on x. But, and I realized this after I left class yesterday because I was playing around with this because I was confused in class, obviously, as we saw. If I repeat the call to internal inspect on x of 1, you'll notice something really interesting, which is that it says it's got a different memory address. Okay, and actually, so this is, I guess, what I mentioned in the in my note on Piazza. So I suppose there are two interpretations here. One is just by querying the value, it's somehow like changing where it's stored in memory. So that seems fairly implausible. And the other is that somehow this is not actually telling me what the memory address of the first position x is. Think about what's happening here. This is actually R code, right? And remember what I said about operators. Operators are basically functions that go in and evaluate R code. So this is really saying internal of inspect of the square bracket function, the square bracket operator, applied to the first argument being x, the x object, and the second argument being the index that I'm supposed to pull out. So have I led you on enough about what might be going on?
Creates a new instance of the function.
New instance of the output, presumably, yeah. So what's probably going on here is this is basically evaluating x square bracket of 1. It's getting the value back, it's not assigning it into any named place in memory. There's no name associated with x square bracket of 1, the result of doing that. But what it's probably doing is putting it in a place in memory. It's sort of an anonymous location in memory because it doesn't have a name of the variable associated with it. And then it's doing internal inspect on that. So it's saying, oh yeah, okay, I went in, I pulled out x of 1 from the vector that was stored here. I put it over there in memory, and now you're asking me where it is. Oh, well, it's over there. And over there is this. But the next time around when I do it again, over there is over there. And so it gives back a different location in memory. So I think there was essentially a bug in what I was sort of playing. I'd actually never done this before, I don't think, until last class. But this, I think, is not doing what I was thinking or hoping that it might do. Okay, any questions about that?
What if you do this third time? You still get
Yeah, I'm pretty sure it's going to give me back yet another. So I have to change x because I've been working with it here. I mean, I guess I don't have to change it, but just for the sake of clarity. Okay, so there it is once, there it is twice, there it is a third time. There, I think I could just keep doing this ad infinitum because every time it's going in and retrieving the value, and there's no reason it would put it in the same place in memory. It just puts it in whatever is the sort of next available place. Okay, were there other questions? Yeah, go on.
But how do you then actually see where the first time is?
Yeah, so that would involve a little. We'd probably have to start to delve into some of the documentation in R and find out a little bit more about how. Remember, I said any R object is a struct in C. So it's basically a struct in C is basically like a list in R. It can hold heterogeneous kinds of information. And so what it has in there is it has the vector of information of the values. It also has this meta information, and the question is just how is it all stored together and what comes first? And we just have to look that up. There might be a way to do it with a more fancy use of this that I don't know offhand what it is. There should be some there is documentation about how R stores objects, and it must be in there somewhere. Okay, so we've already seen this. I want to say one more thing about copies being made with function calls if you write your own C code. So this is not something we're going to do in this class, but it's something that many of you, some of you may have already done, many of you may do in the future. So again, this is just a little toy example. I'm creating a function called silly_exp, and the reason this is silly is because I'm basically writing my own C code to exponentiate a vector and then calling that instead of just calling R's x function. So this is a little bit of use of some other functionality in R for calling C code from R that I'm not going to go into the details of exactly how you do this. It's actually not all that difficult. There are a few different ways to do it. This is one of them. So this little chunk here is actually C code, but it's really just a quoted string in R, and R is just going to treat it as a character string for the moment. And it does a loop in C, and it takes whatever is the input, because of the fact that I'm calling the C function down here, which is an R function that defines a wrapper to some C code, it's going to, I don't actually have to define what the arguments of this little function are because they're basically defined down here, and it says they're n, and x. But basically all I'm doing is I'm looping through the elements of x and exponentiating them. And then the result is I'm going to get the output of that back. And it's basically, on the C side of things, it's still stored in x. But what we're going to see is on the R side of things, there's been a copy made of x. And that's sort of the point I wanted to make here. Okay, so once I've written a little bit of C code as a quoted string, I can basically define a new function that I can use in R by calling the C function, telling it what the arguments are. That's what the signature business is, telling it what the C code is, and telling it sort of what kind of interface to make is to use this sort of .c interface, which, again, I don't want to go into the details. Okay, so that should be, okay, so, okay, so what I'm going to do here is I'm going to run this code. Okay, so I've got vals of 1, and now what I'm going to do is I'm going to call, so this is now basically an R interface to the C function. I'm going to call that with the appropriate inputs. And then I'm going to ask basically where everything is stored. So I'm going to do dot internal of inspect of vals. So that's where that is. Now let me actually call the C code, and then let me ask the question of, okay, so vals is still the same as it ever was. Right? So I've now run the C function. I've passed vals in. You'll notice in the C code, can I still see it? Yeah. There's no actual memory allocation in the C code. Anybody who knows C would realize that you have to call the malloc function to allocate memory. You'd have to call new if you were writing C++ code. But there's been no memory allocated in C. Okay? But if we now look at what out1 is, it is now a list, and it contains the exponentiated values stored in the x element of that list. So basically, I've fed in n and x into the C function, and the output is a version of n and x where the x has been manipulated and modified to do the exponentiation. And so somehow in that interfacing between C and R, we've now created this list, and this memory has been allocated by R to hold the output. Okay. So the result of that is now that...
So is there no memory allocated by C for that? Is C just dumping values straight to R?
Yeah, so basically what I believe what's happening, I'm fairly sure about this, is R is managing sort of the interface into C. R, basically, when R is about to pass the n and the x to C, it makes a copy of the x. C then operates on that copy of the x, and then it's still sitting there in memory. R knows where it is in memory, and then when R creates this list, this is what was operated on by C. It's the copy that was made initially by R before it was passed into the C code.
So R allocates the memory.
Yeah, yeah. R allocates the memory, and C is just using that memory.
I'm going to assume R's memory allocation function is a call back to C.
Yes. Yeah. Yep. And so we could do internal of inspect on out1 of x. This is, of course, going to be a new location in memory. It has to be because these are totally different values than the values that went in before they were exponentiated. Okay, that will come up a little bit in one of the questions on the problem set, this issue of sort of what's happening when I call some C code. So you guys will get a chance to see this again and think about it a little bit more. Any questions at this point? All right, so then there's one last thing I want to say about memory, and then we'll turn to object-oriented programming. So there was this idea when I was just talking a little while ago, that we passed x into that function f, and it was assigned to arg1, but arg1 was pointing to the same place in memory, this little diagram that I had over here. And so this, actually, if I ran this code, that would just illustrate the same thing again. So I don't think there's any real reason to run that. But what I do want to do is show you that this idea that copies are not always made actually happens regardless of whether you're actually explicitly running a function and passing an object into a function. It will also actually happen when we're just assigning things into a new variable. So here I'm going to, I don't know why I keep doing this with such large objects. I must have had a reason for this at the time. Oh, I see. I think it was because I wanted to be able to see the object show up in the garbage collect when I ran GC, so it had to be big enough for it to be sort of obvious as to be standing out. So I don't know whether it's important or not that I illustrate that here, but I'll just restart R so that we have a fresh session. And so now what I'm going to do here is illustrate this in two ways. So I'm creating this vector this vector y. I'm calling GC. I'm looking at the memory address of y. And then I'm calling GC, looking at the memory address of y, and then I'm making a copy of y in the variable named x. And then I'm calling GC again. What pops out at you? I've made a copy of x. I've made a copy of y into x. What happened in GC? It's still 80 megabytes that's currently being used. The maximum ever used is still 80 megabytes. So there must not have been a copy made in any regard, even temporarily. And so basically this same thing is happening just in your global environment, and now we're not even thinking about function calls anymore. Now we've got, actually I guess this was originally started as y. Now I have this thing that I just created as x, but it's really just pointing back to the same place in memory that x is pointing to. So that's nice because that saves a bunch of computation and saves a bunch of memory. Yeah.
The GC trigger
That has something to do with when R goes through and looks to see if there are objects that no longer have a name associated with them and if it can release that memory back to the operating system. I don't know the details of exactly how that works, and it's
It's not related to the copy.
I don't think so. There may be something in the internals of yeah, but I think for our purposes it's not relevant. But
When you remove y, will it still be the value? Will it be
okay, so you want me to remove y? Well, let's actually just first let's verify this. Indeed, it's pointing to the same place in memory. Okay. So I forget. Do you want to go by Daniel or Mao?
Mao.
Mao.
I prefer to go back to Mao.
Okay. All right. There you go. All right. So say again what your question was, Mao.
When you remove the
Y.
yeah, when you remove the y, so will x be still show up as a
Yeah. So x will still exist.
matrix or
Yeah. So let's remove y. GC is going to have to give us the same thing again. I guess we could explicitly do it, but I don't think there's any reason to. And you'll see x is now still referring to the same place in memory. So basically what happened was, what sort of happened was, if we're thinking of this as a memory location, this sort of disappears, and it's really just, maybe having a separate box doesn't make any sense. It's sort of like originally y was this, and x was like this, and now I removed y, and x is fine. And it has to be this way in the sense of otherwise all hell would break loose, like the language wouldn't work. Yeah.
So sometimes we have made a copy of the values, but sometimes we don't. They're in general.
Yeah. So I'm going to get to that in a second. Yeah. I want to also point out something here, just to do a little bit of foreshadowing. The one thing that you might have noticed different here from internal inspect on y and x was this name. This actually stands for name of 1 and name of 2. And what this means is that this location in memory now has 2 names pointing into it. And that's actually how R keeps track of when copies need to get made. You'll notice that when I removed y, this name thing still remained a 2, so it's not actually completely smart about it. It doesn't realize that it can go back to this being 1, like up there. But that's basically how R keeps track of things. I'm not going to go into a lot of detail of how R does it. There's a little bit of detail in the notes if you're interested. Okay, so let's now see what happens if we basically, let's see, do I want to do it this way? I think I'm going to quit R because I think if I present it that way it might be a little more confusing than it needs to be. Okay, so I'm going to create X. Now I'm going to create Y as a copy of X. Sorry, I'm going to create Y as just to try and replicate what I had a minute ago. We know X and Y are now pointing in the same places in memory. I guess I should look and see which ones they are because those places will have changed since I closed R. Okay, so now if I go in and I change a value of Y, now a copy has to get made, right? I've got one vector, 2 names pointing to it, but one of the objects is now going to be distinct from the other one. So if I do it now, I'm going to see that, well, it looks like X is still pointing to that same place as it was before, okay? But Y must be pointing to a different place. And indeed, it is. Okay. And so basically what R did when it did this was it goes in and it says, oh, you know what? There are 2 different names pointing to the same object. That means I have to make a copy. I'm trying to change one of the values of Y, so I'm going to make a new copy of Y, change the value in Y, and the original X is unaffected. Okay. And you'll notice there's now only one name pointing to the memory location where Y is. X still seems like it has 2 pointing to it, even though it doesn't really, and this is sort of some of the shortcomings of R's memory management. And we don't need to get into a lot of the gory detail there, but just to give you a sense of how that works. So I think that may be most of what I want to say about copying and about when copies are made. Any other questions about this? Okay. There's also a function called traceMem. This might very well come in handy. I asked you to do some stuff with memory on the problem set, and so this function traceMem may come in handy, so I'll just show it to you very briefly. So I'm going to create, sorry, I'll do it with y again. I'm going to create my object y. I'm going to do trace mem on y. I think that's basically just saying what the memory address of y is. We could verify that with our old standby here. Yeah, that looks right. So these two are the same. And now if I make a copy of x, and now let's suppose that I do y of 2 gets something else, 4.5. Okay, so now it's giving me a little bit of information to show me that copies have been made. And I think, so we started with EDF10. So it seems to be indicating that something, there was a copy made from that address to this address, and there was also a copy made from this address to that address. I don't actually know why there are 2 here. And if we do internal inspect of y again, it looks like it's now in F48, which is this one. And I wonder actually where is x stored? So that's still stored, like that makes sense. That's still stored in the original FF10. So I don't know what the deal is with this. I don't think there's an entire second copy. I don't think there's an entire additional copy being made of the vector, because that would be a lot of overhead and it wouldn't really make a lot of sense. But something's going on here. So, and I don't know quite what that means. Be an interesting thing to try and look more into in terms of looking at the help information on trace mem and trying to track that down. But I don't know exactly what's going on there. Okay, so I think that's all I want to say about copying and memory. You'll have plenty of chances on the problem set to look into that more. So let me go and talk a little bit about object-oriented programming. Oh, yeah, sorry, Mike.
Is there a function in R where you can put in a memory address and it'll show you what's in there?
So that's a good question. Not that I know of. Yeah. I mean, you can already sort of see that we're sort of delving pretty deeply into the internals of R here, in the fact that that we're using this. In fact, I didn't know about this until 2 or 3 years ago when I was teaching this class, and I was getting confused about what R was doing with all these copies and when it was making copies and whatnot. And so eventually I realized this existed, and then I started to like go around the plumbing and see what was going on. And then yeah. There is a new package that I was thinking of introducing to you guys called. I'm not going to remember the name, but it's by Hadley Wickham, who's developed a lot of R packages, and it's basically a package that provides a lot of functionality for sort of seeing what's going on with the internals. And so I think it has a wrapper that basically calls this, but with a nicer name and some other functionality like that. And so in that package, there might be something like what you're asking about. Unfortunately, since I can't remember the name of it, it's not going to be very helpful to you. But if I remember it, I will let you guys know. And I think it's not yet on CRAN, and it's on GitHub, which is partly why I didn't introduce it this year. But probably next year when I'm teaching it, I'll probably use that instead of some of this. Okay, so object-oriented programming. So how many of you are at least familiar with sort of what the idea of object-oriented programming is? Okay, so about half of you not as much. So that's fine. Okay, so in some ways, you guys, even those of you who are not familiar with object-oriented programming, you've already been doing some of it in some sense, or at least making use of it when you've been using R. And so R is focused a lot around functions, but at the same time, it does a lot with object-oriented programming. And it has a whole bunch of functionality for you to write your own code that uses object-oriented programming ideas. One of the downsides to it is that it's rather more clunky than some other languages like C++ or Python in terms of how it handles object-oriented programming. And it's also clunky in the sense of there are 3 different ways to do object-oriented programming in R, which is probably 2 more than we'd like to have. Be that as it may, it does get used a lot, and it's good to know about. And once you have the idea of how it works in R, it's not going to be very hard to see if you go do some stuff in Python, for example, how the object-oriented programming works in Python. And in fact, I think when Jared talks about Python in section in a couple weeks, he'll probably bring up some of the similarities and differences from what R is doing in terms of Python versus R. Okay, so the idea of object-oriented programming is that we have objects, which obviously we've been working a lot with in R, and different kinds of objects have a class. So different kinds of objects are grouped as a particular kind of class, and they have a particular structure to them. And so this is sort of like if you think about a list. Well, a list can have lots of different components. A class can have lots of different components, and any two objects that have the same class are going to have the same set of components in them. So that's part of this idea of having object-oriented programming, is you have these classes that have particular components to them, and then you can have objects that are members of those classes. But the other cool thing about object-oriented programming is classes can have functions that are associated with them that do particular operations on the object that's of that class. And so the idea is that you would make a class and say it has all these different components. For example, a linear regression class will have components for residuals and what the formula is and what the coefficients are and standard errors and things like that, for example. And then you have methods, and the idea is the methods are tailor-made to work with the objects in the class and to do the sorts of things that you would need to do with those kinds of objects. So examples of those, of classes in R, are the LM and the GLM class. And so what I'm going to do is talk a little bit about the S3 way of doing object-oriented programming in R, and you will see that you guys have actually already been using this a fair amount, actually. So the three different kinds of object-oriented paradigms in R are S3, S4, and something called reference classes, which some people call R5, although I don't think it's supposed to be called R5. And S3 has basically been built into R for many, many years. S4 has also been around for quite a number of years. It's a little bit more structured, and it's somewhat less widely used. And reference classes are new as of 2 or 3 years ago. Okay, so I'm going to go back to, I think I can safely go back to RStudio now that I'm no longer dealing with memory allocation. Okay, so I'm going to call the methods package, because we're going to need that for some of what we do here. So basically all I'm doing here is I'm creating a linear regression and I'm creating a logistic regression with the GLM function. And these are just with some simulated fake data. And I'm going to say, okay, what is the class of those guys? So basically, we've seen both the class function and the type function. The type function has to do with sort of fundamentally how is the object stored in the underlying C code and what kind of object is it in C. And class really has to do with sort of higher level user level information about what kind of object it is. And in fact, this comes directly into knowing what the class is in an object-oriented way. So if I say, what's the class of mod 1, which was the LM, it'll say, oh, it's of class LM. And if I say, what's the class of mod 2, which was my GLM object, it'll say, oh, that is of class GLM and of class LM. And so the idea is we can have inheritance of these classes, that the GLM class is sort of a class that's built on top of the LM class. The LM is sort of the base class. And GLMs you can think of as just LMs. They're sort of more complicated and have more things going on. So it makes sense that we build these things in this nested or hierarchical way. And basically any S3 class in R is basically a list with an attribute that says what kind of class it is, and then potentially some methods that are associated with the class. So I can say, is mod 1 a list? And how did that get in there? And I'll say, yeah, indeed, it's a list. But we already asked, and it said it was also an LM. So it's sort of multiple things all at the same time. Okay, and we can ask that when we say what are the names of mod 1, it's basically saying what are the components, what are the data or the information. Maybe I shouldn't use data because we usually think of data as being statistical kind of data, but what is the information that are stored within an object within the mod 1 object? It has these particular things, and anything in the LM class should have these same elements within it. Okay, and they're the sorts of things you would expect for a linear regression.
When you look at the names of and you get everything that's in that class, are all of these things sort of analogous to attributes and methods? Sort of, they're not all the same. They're not all doing the same thing necessarily. So we're not getting just.
Yeah, they're actually not. So they're not even really directly tied in with methods yet. We're going to see what the methods associated with an LM are in a second. And and in some ways they're not really attributes either. The attributes of let's actually do that. That will maybe be illustrative. If we say what are the attributes of mod 1, it says okay, it's basically just the name of the class of the object, and then just the names of these objects that are in there. But the residuals themselves, the numeric residuals, are not part of the attributes. This is just saying there's an object called residuals within the object, or an a component called residuals within the object. And then if we actually want to look at the residual values, then we would just pull it out with mod 1 $ residuals, just like we would if this were actually a list, which it is. Other questions?
So all numbers in R are stored in C data, correct?
Right.
So
As vectors,
all
yeah.
numbers in R are actually objects in C.
Yep.
Okay, so there's nothing in R that isn't technically an object.
No. Yeah.
It's not object oriented.
Okay, so then sort of getting back to my response to Brianna's question, if we want to know what are the functions that we can use on an LM object, or the methods that are associated with an LM object, we can use the methods function, which I think is in that methods package, which is why I need to load it in 5 or 10 minutes ago. We can say, what class am I interested in? And if we do this, it'll say, oh, there's a whole bunch of things you can do with an LM, some of which may not be totally obvious, but some of which are going to be sort of blindingly obvious. There's a formula, there are hat values, there's a log likelihood associated with model, there are DF betas for doing residual checks and things like that, a lot of the sorts of things you would expect. So these are all functions methods or functions that I can call on an LM object. And part of the reason, I think at some point I've said it's probably bad practice to name anything with a dot in it. Part of the reason is because this dot here means a very special thing. What this is this is the influence method for the LM class. And if I type influence.lm, I might need to go and tell it in the stats package. Okay, it should be in there somewhere. There we go. Turns out what is it doing here? Oh, yeah, that's interesting. I didn't know that. Why did it? Yeah, so apparently it's now just calling a function called lm.influence, which seems a little odd, but that's what it does. Okay, so eventually we sort of got our way in here and saw this is the actual code that gets executed if you call the influence function on an LM object. But the other thing to realize is we don't actually need to, hopefully this is what I meant to say next, we don't actually need to call influence.lm on that model. And in fact, we couldn't because, as we saw, it was sort of hidden from our view. It's sort of buried in the namespace of the stats package. But we can call influence without the .lm on mod 1, and it'll return back whatever the influence values are, which I've sort of forgotten what their definitions are, but in any event. So if we look at the code for influence, what we'll see is it has this special function call called useMethod in here. And so this is where basically what's called method dispatching is going on. So when we call influence on LM, what happens is this function gets called, and it basically goes and tries to figure out there are potentially a whole bunch of different influence functions. There's probably a different one for GLMs than there is for LMs. If you ran a generalized additive model, there would be a different influence function. And so what this does is it goes and says, what kind of object are you feeding me? And I'm going to then go to look for something called influence.lm because you're feeding me an LM object. Okay? So basically this dispatching has to happen, and this is called the generic function, and influence.lm is the class-specific method that gets called when this generic method is called on an object of the LM class.
So whenever if you were to create an object yourself, yourself. You would have to create an instance of influence dot your object name
Right.
in order for that to work.
Yeah. So if I let me see if I want to. Yeah. So let me show you a little bit of an example. So I'm not gonna. Okay. So I'm gonna create an object in the bear class. Of course, the most famous bear is Yogi, so that's the bear I'm going to create. So all I did to create this object was I first made a list and assigned it some information about this bear. And then S3 is really, really informal. So all I have to do basically to make this object into something of the bear class is just say the class of it is a bear. Okay. And we could make functions that basically are something called a constructor, which basically creates a bear object. And this is basically how you would do that. You'll have a chance to do this in the problem set, so I'm not gonna. And it's just syntax, so I'm not gonna bother to spend a lot of time on it. But in terms of answering Daniel's question, here's another example where I'm going to create. These are two different. Again, this is just an LM and a GLM. They're different names for reasons that are probably not. I probably should have just named everything the same. This is just an oversight on my part. But you'll notice I call summary on mod and I call summary on gmod. And what's happening there is in both cases the summary function is getting called, but in one case it's going and then calling summary.lm, and in the other case it's going and calling summary.glm. And your question, Daniel, is basically, what if I wanted to call summary on the bear? Would I be able to create a summary.bear function that would somehow give out summary information about bears instead of summary information about LMs? And you can do that, and I think if the generic method, the summary function, already exists, then I wouldn't have to write summary. I would just have to write summary.bear. If the generic function didn't exist, then I also have to write the generic function as well as the specific function, and that's what I'm illustrating here. So just for the purpose of illustration, I decided to make something called summarize instead of summary. So this is creating the generic method, and then if I want to be able to say summarize on my bear object, which I called Yog, then I would have to then write a summarize.bear. It'd have to take in an object, and it would have to do whatever. It would basically have to be the code that provides me with whatever it is that information I want to spit out back to the user. So in this case, I say, the bear is of a certain age and blah blah blah, and then I can call summarize on the object in the bear class, and it'll work.
So really, summarize is a wrapper that just enables you to access the summarize dot function.
Yeah, it's just a wrapper. People call it method dispatching, but either one of those ways of describing it. I guess I didn't create my particular bear object. In any event, this code will work if you want to see it in action. You can run it yourself. Okay, we can also create operators that will work on objects in a class that we create. So I could create a plus object, and I could add a number to my bear, and as long as I've written an operator that will do something meaningful here, this code would actually work. That code does work. I can create my own replacement functions that work with objects in my class. Again, I'll let you guys look at this syntax on your own. And let's see. So I think I want to say one more thing about this, but before I do that, are there any questions so far? Yeah,
Sorry,
go
I'm
on.
a little confused with so when you do the plus, so is it basically making a new thing that encompasses the old class and then
Yeah, so with S3 objects, reference classes are somewhat different, but S3 objects and S4 objects and like R objects in general, if you modify the object, you're going to be making a copy of it and returning a new copy of that object. So basically, whenever you write methods like this, what has to happen is you're basically going to write the function, it's going to take in the object, you're going to modify the object. As soon as you modify the object, a new copy is necessarily going to have to be made.
this is not the old class.
This is not the old...
The plus, like the addition. Or is this?
Okay, maybe I was answering a question differently than the one you're actually asking. So this is defining a plus method specific to the bear class. Like the normal plus method is you add together two numbers.
Right.
But here I'm defining a plus that will work with Bayers.
So you are not messing with the old class.
I'm not messing with the old one. Yeah. This is just, and it actually happens again by this method dispatch, which is when R sees a plus, it goes and said, what are the things you're trying to add together, and then it goes and finds the right plus function. Yeah. Anyway, to answer the question you weren't asking, then you return the object. This is a new copy, and so here's the old object. I modified it by adding 15 in this case to the age, and here's a new object that is a new copy of that bare object with some modified information. Okay, so the last thing I wanted to say about these S3 objects is anytime that you at the screen anytime I do something like y gets R norm of 5 and I type y here, what's happening is not what's happening behind the scenes is a function's getting called. You probably did not realize that, but this is the same thing if I do print y. And in fact, the R interpreter, when it sees this, it actually goes and behind the scenes goes and calls print on the object. Okay? And so that's another way in which basically any operation you're doing in R is just a function call. It's just you may not realize it from the syntax. And the other aspect of this is you can write print functions that are specific to classes. Okay, so print of y didn't do anything particularly interesting, but remember I had an LM object called mod. If I do print of mod, it's going to do the same thing as if I just type mod. And you'll notice if we now look at it in this in sort of the light at which we're considering things now. Remember, we already saw that mod was a list, but it's also one of these LM objects. And you'll notice in the printing out, this doesn't look anything like what happens when we print out a list, right? If we print out a list, A is list of B equals 5 and D equals 7, and now I print out A. It has it has all this thing with the dollar signs and the brackets and everything. That mod didn't look anything like that. So the reason for that is there is a print.lm method that when you call print on an LM object, it prints out information in a particular structured way, which is the way that you're seeing here. And we should actually be able to see what the print.lm method is if we force our way deep enough into the guts of R to see it. So here I went into the stats package. That's where print.lm is defined, and you can see here's actually what it does to do that printing out. Okay, so just another lesson in everything being a function call, and in this idea that we can define methods. I could define a print method for my bare class and print things out in whatever way I want to print them out. Yeah, Joe.
I have a question about that. That last thing. So what we did was to define another class-specific, bare class-specific class method. And why want to remove that so we don't end up messing whatever's reading?
Yeah, we don't need to worry about it actually, and that has to do with R's dispatching of the generic plus operator. I can still say 5 plus. Well, I'm not even sure whether I ran this code. So let me actually run that code. Okay. So, but now if I do 5 plus 5, it still works, and that's because when R is interpreting this, it says, "Oh, you want to do plus." What are the arguments you're feeding the plus? Oh, they're two different numbers. I'm going to go find the plus that operates on numbers. Whereas if one of these was the bare object, then it would go find that one. So you don't have to worry about removing it. Yeah, and anyway, when I quit the session, the bare one is going to disappear anyway. Okay, so let me take 20 more seconds of your attention, and I'll restate this on a Piazza post, but because it's out, I'm going to ask you to do something for Monday, which is I have a little brain teaser for you to think about the sort of test whether you're understanding this business here, which is what I want to do is when I type Q at the prompt here, I want R to quit without asking me anything or doing anything else. I just want R to end its session and disappear. Well, right now, if I type Q, it says, oh, that's a function, and you have to tell me whether to save the .8R data file and whatnot. So I want you to see if you can figure out if there's a way, if I just type Q, for R to close, and think about what we just talked about in terms of printing and objects, and see if you can figure that out. And I'll restate the question on Piazza as well, but think about that for Monday. Okay, so I'll see you all on Monday.
Did